You know, we see squares and cubes everywhere, in buildings, in art, even a simple cardboard box. But what if I told you there's a secret hidden inside them, a kind of mathematical code written entirely in the language of odd numbers? Today, we're going to dig into the grade 8 Ganita Prakash textbook to uncover these incredibly elegant connections. So let's back up for a second. We all know that a number multiplied by itself gives you a square number, right? But is that really the whole story? What truly makes a number a square? Let's start with the absolute basics to really get this. The easiest way to think about square numbers is, well, as the area of an actual square. A square with a side length of 1 has an area of 1. A side length of 2 gives you an area of 4. Side length of 3, you get an area of 9, and you see where this is going. This is our foundation. But these numbers, they have a special name, and that's where we find our first clue. They're called perfect squares. Now, the textbook defines them as just the squares of natural numbers, which, okay, sounds simple enough. But hidden inside that very simple definition is our first major clue to a much, much deeper pattern. Okay, now this is where things get really cool. It turns out that perfect squares aren't just the result of multiplication. You can actually build them piece by piece using a very specific and, well, beautiful sequence of numbers. Let's start at the very beginning. The first odd number is 1. And hey, what's the first perfect square? Also 1. 1 squared. Simple, right? But just watch what happens next. So, what if we take that first odd number, 1, and add the next one in line, which is 3? Well, you get 4. And what's 4? It's exactly 2 squared. You starting to see it? Let's keep going. We take the sum we just had, 4, and add the next odd number in the sequence, that's 5. The result, 9, which is, you guessed it, 3 squared. The pattern holds. All right, one more time, just to be sure. 1 plus 3 plus 5 plus the next odd number, 7, gives us 16. And of course, 16 is 4 squared. This is no accident, folks. This is a fundamental property of numbers. And this leads us right to the big reveal from our source material. The sum of the first n odd numbers is equal to n squared. It's a simple, elegant relationship hiding in plain sight. And this isn't just a neat party trick. It's a tool we can actually use. Okay, so why is this important? Well, think about it. If we can build a perfect square by adding odd numbers, that means we can also test if a number is a perfect square by doing the exact opposite. And that brings us to this really clever method called successive subtraction. Instead of building up to a square, we're going to break a number down to see if it's got that square DNA. Let's try it out on the number 81. First, we subtract the first odd number, 1. That leaves us with 80. Next, subtract 3, we get 77. We just keep doing this, subtracting 5, then 7, then 9, taking away each odd number one after the other. The whole point is to see where we land. And with 81, we keep going and going all the way down to 0. But here's the kicker. The really important question is, how many times did we have to subtract to get there? If you go back and count the steps, it took exactly 9 of them. And that right there is the magic. Because we landed exactly on 0, we know for a fact that 81 is a perfect square. And the number of steps it took to get there, 9, well, that's its square root. How cool is that? A beautiful, practical application of our hidden pattern. So, okay, we found this incredible link. Squares are built from the first odd numbers. But is that the end of the story? I mean, what about cubes? Do these fundamental building blocks of 3D space also have some kind of secret relationship with odd numbers? Oh, you better believe they do. But the pattern for cubes, it has this amazing twist that connects right back to what we just learned about squares. Just look at this. The first cube, 1 cubed, is just the first odd number, 1. Okay, easy enough. But look at the second cube, 2 cubed, that's 8. And get this, it's the sum of the next 2 odd numbers, 3 plus 5. Whoa, what about the third cube, 27? It's the sum of the next 3 odd numbers, 7, 9, and 11. The pattern just keeps on going. 4 cubed is the sum of the next 4 consecutive odd numbers. Okay, let's put these two ideas side by side because this is just beautiful. For perfect squares, you add up the first n odd numbers to get n squared. Simple. For perfect cubes, you add up the next n consecutive odd numbers to get n cubed. It's just so elegant and symmetrical. The same building blocks, odd numbers for both. So, what's the big picture here? What does this all tell us? It tells us that squares and cubes aren't just these separate, isolated ideas. They're part of a much bigger, interconnected world in mathematics, the world of powers. You see, n squared and n cubed are really just the beginning of the road. This whole idea of multiplying a number by itself over and over, that's called exponential notation, and it can go on forever. N to the power of 4, n to the power of 10. It's a powerful shorthand for talking about massive numbers. And as we've just seen, it has these beautiful hidden structures inside. You know, finding patterns like the one we saw today does exactly what the foreword of this textbook was getting at. It helps to show the connectedness and unity of mathematics. These aren't just a bunch of random rules someone made up. They're all pieces of this huge, logical, and honestly, beautiful puzzle. So, after all of this, what's the big takeaway? We've seen that the simple sequence of odd numbers, the ones we learn about as kids, are the secret foundation for both squares and cubes, and in this deeply connected way. And it really makes you wonder, right? If a pattern this elegant is hiding in plain sight, and something as basic as a square, what other incredible secrets are just waiting for us to find in the numbers all around us?